So this is lesson 2 in our calculus unit 6 on introduction to limits and the power rule for derivatives, one of the most famous topics in calculus. So our lesson goals for today is that you should understand the concept of a limit and you can identify limits from a graph or a table. The formal analytic or algebraic calculation of limits is not in the SL course, which makes it easier for us. You should be able to use the power rule to determine a derivative function of a polynomial term with integer exponents. And you can use the derivative function to calculate and interpret the gradient of a function in a variety of contexts. So let's get started with what is a limit? Well, suppose that by letting x get sufficiently close to, but not equal to, some value a, we can make the function f be as close as we like to the value a. And we say that the limit of f of x approaches a is a, and we write that the limit of as x approaches a of f of x is capital A. So that's sort of the formal way just to say, follow the pattern. If we have our x values are approaching 2, what's supposed to go in this blank? 3.9, 3.99, 3.999, 4.1, 4.01, 4.001. What clearly goes here? It says that the value is undefined. That's because there happens to be a hole in this line. And that's because if you took the equation that's represented by this table and by this graph, if you actually evaluated 2, that would be 2 squared minus 4 is 0 on the top, and 2 minus 2 is 0 on the bottom, and so 0 divided by 0 is called an indeterminate form. We actually can't really evaluate this function. But a limit is not what is the function literally, but where is the function approaching? What does the function want to be? And clearly, the limit as x approaches 2 of f of x clearly equals what? 4. Obviously, this function clearly wants to be 4 at x equals 2. So that's the idea of a limit. A limit is what does the function want to be as x gets sufficiently close to, but not equal to a function value. All right. A derivative. We talked about this last class. A derivative is a function for the slope of another function. With limits, a derivative is a limit of a slope of a tangent line. For the curve y equals x squared, here are the slopes of some secant lines, which we called a secant line, we've been doing this for the last couple classes, the average rate of change of a function. And with this parabola here, I just have a bunch of examples of these lines that are actually found by using the Algebra 1 slope formula starting at x equals 1. X equals 1. And so we can calculate some average rates of change, some average rates of change using the Algebra 1 slope formula. So for instance, if we do 3 squared minus 1 squared all over 3 minus 1, that's the Algebra 1 slope formula to find the slope between 1 and 3, and that slope is 4. Between 2 and 1, that slope is 3 if you use the slope formula. The slope formula at 1.1, so we're getting closer and closer to 1, the actual derivative at 1, we get a slope of 2.1. And then if we use 1.01, we get a slope of 2.01. And eventually, we can't actually do just 1 squared minus 1 squared all over 1 minus 1, because that would also get a 0 over 0, just like in the last slide. So we can't actually find the slope at a point using only one point. So even though we technically can't plug in 1 into the slope formula, because we'll then be dividing 0 by 0, we can clearly deduce that the slope is approaching 2. Therefore, the derivative of x squared at x equals 1 is 2. because those secant line slopes are clearly approaching 2. Therefore, the slope of the tangent line right at 1 is clearly 2, even though we can't really calculate that. But that's what the essence of a limit is. It's using your pattern, your reasoning skills to make that logical leap, which is so obvious based on the pattern, but technically we can't evaluate that. All right. So, more formally, and we don't use this formula in the SL course, so this is just so that you're aware of sort of where this all comes from, although we won't use this. The derivative f prime of x of a function f, which represents a formula or a function for the gradient or slope of f at any x value, is this formula right here. And what is this? This is the limit as some h approaching 0, which represents that the distance between 2 points becomes 0 in the slope formula. This kind of looks like f of b minus f of a all over some b minus a, which we're now calling just h, which basically just represents that we have the slope formula here, but we don't have 2 points anymore. We only have 1 point. Now, the technical application of this is outside of the scope of the SL course, but if you're interested, just so that you're aware of how this derivative formula can be applied, again, don't get scared by this. We don't do this in the SL course. If you want to find the derivative of 3x squared using this formula, you can try to follow along here and find that the derivative of 3x squared is 6x. That's going to be our goal. Is that there's a much easier way called the power rule, this famous idea that this lesson is based off of, for how do we know that the derivative of 3x squared is 6x? Because that means the slope of a function, that parabola 3x squared, is 6x. And so we're going to sort of jump right to the power rule, because there's a very, very quick way we can do that without all this formula work that is outside of our course. Okay, so amazing. The power rule. Fortunately, applied in the real world, that derivative formula that we just got scared by can prove some much easier patterns to help us calculate derivatives. So let's cut right to the chase. The derivative of any term in the form of x to the n, and so x to the n just means any monomial, a monomial that is in sort of polynomial form, like x to the 5th, or 6x cubed, or negative 2b to the 12th, or 5 times n to the negative 2. These are all examples of monomials or terms that can be found with the derivative by this rule here. So the derivative, and this notation here is sometimes sort of the command. This is the command. The command. This is pronounced d dx. It's just pronounced d dx. D dx is means that command ddx means take the derivative. Means take the derivative of. You need to have that memorized. So if we take the derivative of x to the n, like x to the 5th power, here's what that says. We take the exponent. So here are some steps for the derivative. Write this down. We, one, subtract, or actually, let me do this step first. We're going to bring down the exponent. So what does that mean? We have x to the 5th power, and we're going to subtract that from 1 after we bring down the exponent. So that 5, if we take the y equals x to the 5th, y prime, or the derivative, is going to be, we bring down, so if you're writing down x to the 5th, kind of circle it. I like to think of it as sort of literally like pulling it down to the left. And then step two for the power rule is subtract the exponent by 1. Okay, so those are the 2 steps of the power rule. So what does that mean? 5 times x, subtract 5 by 1, which is all to the 4th power. And that's it. That's the power rule. That's the whole thing. Amazing. So step 1, bring the exponent down. Step 2, subtract by 1, and you're done. And that's calculus. Okay, let's try another one. 6x to the 3rd power. Remember, there are some different notations used for taking the derivative, and these notations typically come from different mathematicians from different parts of the world that use different notations. So you may see if f equals 6x cubed, we might say that f prime of x equals, and then here we go again. We're going to take the 3, the exponent of 3, bring it down. But what does that mean? We're going to multiply now. 6 times 3 after we bring the 3 down is 18. So we'll have 18. And then what's left? X, and then 3 minus 2 is 2. So 18x squared. Yay. Okay, here are a couple more examples, okay? Just to kind of show you some other notation, we talked about how this command ddx is sometimes used instead of the prime notation. So taking the derivative can be called f prime or y prime or a prime if you see that little apostrophe. However, you may see with this alternate notation, and so this is called Leibniz notation. Leibniz is a famous mathematician. If you're interested, there's Lagrange notation is the prime notation. But you may see the Leibniz notation. So what would that be? The derivative of a with respect to b, is written down dA dB equals. So instead of a prime, you may see dA dB. Or in other words, like your y value, dy dx, you may just see the dependent variable on top, and then you may see the independent variable on the bottom, okay? So then the power rule then is bringing down the 12, so we'll have negative 24, and then b all to the 11th power. Whoa. Okay, very easy, very cool power rule. So let's see if there's a negative number. Negative number, same exact thing. So we have m, so let's find m prime, or I could have said dm dn in this little fraction format. So m prime is, we bring down the negative 2, that kind of collides with the 5, and they join together, holy matrimony, we got negative 10. All right, times n. Okay, now you gotta go the right direction, right? Negative 2 minus 1 is actually negative 3. Okay, not negative 1. So just be careful with your negatives. That's one way this could get a little tricky. Okay. All right. So there we go. We got the power rule. Yay. So that's a really, really big skill for today. The power rule for finding derivatives, which represents the slope of a tangent line at any point. This is a formula that can calculate slopes. All right. I want to address this idea of negative exponents a little bit, okay? Because we don't do a ton of algebra in our course, but you do have to remember this property of of the negative exponent. Okay, you may see, instead of a negative exponent, sometimes you'll see this term written in the form of 5 over positive x squared. Okay, so 5 times x to the negative 2 is actually equal to 5 divided by x to the positive 2 by definition. By definition of negative exponent, dividing a monomial with a positive exponent is exactly identical to that base raised to a negative exponent. So if that sounds kind of weird, then just kind of seeing a few examples is going to really illuminate this. So 3 times x to the negative 6 is equal to 3 over x to the positive 6. 5 times, or 5, let's do divided by x to the 7 is equal to 5 times x to the negative 7. Also, 3 all over 2x to the 5th power is equal to, well, we have just that 3 halves, and then times x to the negative 5th power. Okay, so this is important for you to understand, because sometimes in IB style problems, you'll see the fraction form of a monomial, but the power rule does not work with quotients or fractions. So you'll have to rewrite it into this negative exponent form so that you can do this amazing quick formula, the power rule. So if it's in fraction form, you have to convert it to negative exponent form first before you do the power rule. All right, so that's a reminder about negative exponents. Let's then look at examples where we have like multiple power rules in a row. So if you have 1 term, 2 terms, 3 terms, you have to understand that taking the derivative just kind of like distributes the derivative. You can do the first term and then do the power rule on the second term and then do the power rule on the third term. So if you have 3 terms, this is going to be 3 power rules that we're going to do, just one after the next. And so let's look at this middle term, which is called a linear term, because a linear term is one that looks like a line if you graph it, like negative 3x. And then we're also going to look at constants, like 1. So constant and linear terms and their derivatives. So remember, the derivative is a slope. So the derivative of linear terms like 2x, 5x, or negative 4x are simply their slope. So the derivative of negative 3x then, the derivative y prime is negative 3. Now, if you're wondering why this works, well, not only does it kind of just make logical sense because a derivative is a slope and the slope of this line is negative 3, but also it still works with a power rule. If we have y equals negative 3 times x to the first power, the derivative is we take that exponent, bring it down, so that's going to be negative 3 times 1 is just negative 3 times x to the 1 minus 1, which is 0. But any term raised to the 0 power is 1. So therefore, y prime is just negative 3 times 1, which is just negative 3. Okay, so that's sort of the power rule proof for why linear terms have a derivative that's just their slope. Intuitively, it's because slope means derivative, but the actual working of that makes sense as well. So then, kind of naturally then, horizontal lines like y equals 1 has a slope of 0. The derivative of every constant is 0 because the line 1 has a slope of 0. So therefore, the derivative of this trinomial, we have 3 power rules. So this squared comes down, and 1/4 times 2 is going to be 1/2. And then x, because x squared, 2 minus 1 is 1. And then the linear term, negative 3x, is going to have a derivative of minus 3, which we just showed here. And then the 1, this derivative is 0. So we don't have to write anything for the third term. So if you have a constant, the derivative is just 0, so we don't write anything there. And then, well, that's it then. We now only have 2 terms, and here is our derivative. Yay! Okay, so there we go. We had 3 power rules. Linear terms are just their slope. Constant terms, the derivative is 0, and we're good to go. So that's constant and linear terms. Let's look at just a few more examples, but we'll also calculate gradients at a point. Okay, gradients at a point. What that means is, step 1, take the derivative. So find y prime. Step 2, we're going to plug in an x value. Okay, so we want to find the slope of these functions at x equals 2. So we're going to find the derivative and then plug in this case, 2, and just see what we get. And that finds us the slope of this function. Okay, so y prime is, bring down the 4. That's going to be 12, and then we have x cubed. And then we're going to plug in 2. So this is written y prime of 2 equals 12 times 2 cubed. Okay, so now we got to do 2 cubed. That's 8. 2 times 2 times 2 is 8. 8 times 12 is 96. That's a really steep line. Like, think about what a slope of 96 is. Like, y equals 96x is like a really, really steep line. But that's the slope of that function at 2. Okay. The next one, number 2, y prime is 15x squared. And then if we plug in 2 to this, y prime of 2 is, well, that's going to be 15 times 2 squared, which is 15 times 4, which is 60. All right. Let's keep going. We have y prime is, in this case, we have the 2 gets multiplied with the 2. That's going to be 4x plus 3. We have more linear terms here. The slope of 3x is 3. The slope of a constant is 0. So that the negative 5 doesn't have anything for the derivative. Okay, and then we have y prime of 2 is 4 times 2 plus 3, which is 11. Okay, next one. We have y prime. That's going to be 3x squared plus 2. Again, we have the linear term and the constant. So the linear term slope is 2. The constant slope is 0, so we don't have anything for the derivative there. And now let's plug in 2. Y prime of 2 is 3 times 2 squared plus 2, which is going to be, let's see, 3 times 4 is 12, plus 2 is 14. Sweet. Aha, we have one of those fractions. So we have to remember that 2 divided by x to the first power is equal to 2 times x to the negative first power. Remember that negative exponent definition. And then we'll have plus x. So we haven't taken the derivative yet, but now we'll find y prime. So how do we do that? Bring down the negative 1. That becomes 2 times negative 1, which is negative 2, x. And then negative 1 minus 1 is negative 2. And then we'll have plus the slope of the line y equals x. That's a linear term that just has a 1 in front of it. So the derivative of x, you need to have this memorized. Write this down. The derivative of x is 1. Because the slope of y equals x is 1. Okay, so now we'll evaluate y prime of 2. That's negative 2 times 2 to the negative 2 plus 1. Well, what is that? 2 to the negative 2 is 1 over 2 squared, which is 1 over 4. So that's going to be negative 2 all over 4 plus 1. And that's going to be negative a half plus 1, which is positive a half. Now, you would have your graphing calculator to help you with any of that fraction work if you need it. Okay, and then for number 6 here, remember, anytime we have a fraction, we need to convert it to negative exponent form. So y equals 3 times x to the negative 2. And now let's take a derivative. Y prime equals, bring down the exponent. That's going to be negative 6 times x to the negative 3. And then we'll have y prime of 2. Not bring down. We're not going to do a second power rule. That's going to be negative 6 times 2 to the negative third power, which is going to be negative 6 all over 2 cubed, which is 8, which is negative 3 over 4. Okay. So at this point, if we were in class, we would normally sort of pause and ask for a takeaway or a question. So pause this video and process what are the most important parts of this lesson so far, and be ready to share them next class or any questions that you have. Okay, I just waited for 4 seconds and you probably didn't pause the video. But anyways, let's keep going. All right, let's talk some calculator skills. So you can verify your answers using your graphing calculator. So we just did this problem that we found that the slope was negative 3/4 or negative 0.75. There are 2 ways we can use our graphing calculator to calculate derivatives at a point. And so let's do both of those now. We can, in a graph, let's graph this function. We had 3 over x squared, 3 over x squared. So I'm going to type 3 divided by x squared. And we can go to second calc derivative, which is really great. Second calc. So I did second. Now I'm going to go to calc. Now we go down to the derivative. There it is. We've never used the 6 and the 7 before. We've only used 1 through 5. Here we go, the derivative. And then it wants us to type in the number we want to find the derivative at. And we were just, we've been plugging in 2 to all of our derivatives. So let's just type 2 to calculate the derivative. We do second calc derivative, and then we have to type the x value we want. So 2, and then 2 shows up, and we have to hit enter. There's our derivative, the negative 3/4 that we just got from our doing it by hand. Our calculator can find this for us as well. On the home screen, we can do this on the home screen as well. Second, quit. We're going to go to math. Math. And we go down here, it says n deriv. So this is how we find a numerical derivative. That's what that stands for, numerical derivative. So we're going to go down to n deriv. So we did math, n deriv, hit enter. And it asks for some information, okay? And so remember what some of our notation is, what our notation is. We have this notation for the derivative d dx. So what you type in here is just the x, is just x. Your calculator does this because technically there are other variables that you can use here, but the standard variable is just x. You won't type y or you won't type a. If you ever see a different letter, your calculator only knows x, so you'll only ever type x here, okay? Now here, whatever your function is what we're going to type in next. So we had 3 divided by x squared. And then we go over, we hit the right arrow button so that we bop over to which x value we want to plug in. And remember, we were typing in 2 for this. So we'll type 2, enter. And there we go. We get our negative 0.75 again. It has a little bit of rounding error, but don't worry about any of that. Your calculator is technically doing an approximation using a lot of sophisticated calculations to get this negative 0.75. But you just need to recognize that as negative 3/4. So let's interpret that answer. The instantaneous rate of change of y at x equals 2 is negative 3/4. This also means the gradient or slope of the tangent to y at x equals 2 is negative 3/4, or just the derivative of y at x equals 2 is negative 3/4. All 3 of these may be how you may be asked about this on the IB exam. It may not say find the derivative at 2. It may say find the gradient of the tangent to y at 2. So you just have to understand that all that means find the derivative, plug in a number, and you're good to go. Okay, back to business here. Sometimes you'll need to use a little bit of algebra like the distributive property before using the power rule, okay? So watch out for this because you cannot perform the power rule unless your expressions are sort of in like a normal polynomial format, like for instance, like y equals x to the 5th plus 3x squared minus 7. Okay, so you need to have like clear terms that are sort of all spread out before you can use the power rule. So if you don't have power rule yet, you may need to use the, for instance, this idea of the distributive property of fractions, for instance. So let's distribute this x out, or the divided by x. So that's going to be x squared all over x. And then we'll have plus, we have the 4x divided by x. So we'll have 4x divided by x. We have the negative 5 divided by x. So we'll do minus 5 divided by x. So we're using the distributive property to distribute the fraction of the x. So how does that help us? Well, x squared divided by x, one of the x's in the one x in the bottom cancels with one of the x's in the numerator. So we'll have just x. X squared divided by x is x. And then we'll have plus x divided by x cancels. So we'll have just plus 4. And then we've seen this one before. This is negative exponent. This is going to be minus 5 times x to the negative 1. Okay, now this is a format that we can actually do the power rule with. So we'll have y prime equals, well, if this is y, it wasn't defined. Oh, there we go, now it is. So the derivative of x is 1. The derivative of 4 is 0. And then the derivative here, the negative 1 comes down. That's plus 5 plus 5x to the negative 2. Some textbooks, you'll see this sort of rewritten so that we don't have any negative exponents. That's kind of like a sort of the most simplest form to not have any exponents. So we may see 1 plus 5 over x squared. 5 over positive x squared. Write that a little bit better. Okay, there we go. So you may have to do the distributive property before you can do the power rule. So here is, we're going to go over two sort of applied examples that you can see kind of IB style, how this might get a little bit more tricky, okay? So we're going to see two examples. The first one is we have this equation here, and we just want to find the derivative first. And that's kind of a normal sort of power rule, right? So we have the 4, and we bring that down. 3/8 times 4 is 3/2. And then the 4 subtract 1, we get 3. And then the derivative of negative x squared, bring down the 2, subtract 1, we get minus 2x. And then the derivative of 5 is 0. So part A is exactly what we've been doing with the power rule. But then in part B, this is sort of the application part. It says the gradient of the tangent to the curve at a point is 8. The way that you have to interpret that is what that means is the derivative, or y prime, equals 8. So that means you need to really understand this. Set the derivative, set y prime equal to 8 and solve. Okay, so right here it says we let the derivative equal 8. And here's the derivative. The derivative function equals 8. And then we solve this, okay? And then, and there are a couple of different ways to solve this. We're not going to do too much crazy algebra with this in our course, but if you were to solve this by hand, I would probably suggest you instead just solve this in your calculator. And the way that we can solve equations in our calculator, there are a couple of ways, but one way that we've talked about that I really stress is the graphical approach with the intersect button. So that's going to be 3/2 x cubed minus 2x, and then we'll set that equal to 8, okay? And when we graph that, here's what it looks like. Boom, there's our intersection point. So you're just going to go to second, calc, intersect, and then go to the intersection point, and then do your first curve, second curve, enter by just hitting enter 3 times. Enter, 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 boom. We have the point 2, 8. And let's see, this, it looks like this answer key is incorrect. Oops. Oh wait, no, it's not. So this is this intersection point x equals 2. This intersection point x equals 2 is the x location of your derivative. But the reason why the calculator was actually correct, and this one is correct, it says find the coordinates of the original function. Find the coordinates of p, which was the original function. So we have to substitute that x equals 2 back into the original equation, not this derivative function. The derivative function is not the original function. The derivative function is the slope function. That just told us the x coordinate. So we're actually going to substitute this x value back into the original equation. And so if we do that, we're actually going to look back at y. So that x equals 2, goes back into your original function to find the coordinates of the point where the tangent to the curve has a gradient of 8. And so when we substitute 2 back in, we just get 7. And so the coordinates are 2, 7. So that's one application of, if we have a derivative, we set the derivative equal to that slope, and then we solve an equation, and then we had to find an original point, and then so that then we get the point where the tangent actually does have a slope of 8. Okay, so there's one example for an application. And putting this into a real world context, this actually is going to be a lot easier, these word problems, because we're just going to take a power rule and then we're going to interpret our answer. We have here the daily cost of production of a company producing lithium batteries is modeled by this function, where X is the number of lithium batteries produced and C is the cost in US dollars. The first problem, part A, is not calculus. It just says find the daily cost of the company if they don't produce any batteries. That would be very sad. Not producing any batteries. Wah, wah. Not a good day. So substituting 0 into the cost function, well, if you didn't make any batteries, here's what your costs were. You apparently still have some cost, even if you don't produce any batteries, because maybe you have some fixed costs of like the electricity bill, you have to pay people salaries and everything like that. So not producing any batteries, just put 0 in for everything, and we get $900. Okay. And then in part B, the marginal cost of production is the cost of producing one additional unit. This can be approximated by the gradient of the cost function. The gradient means the derivative. Find an expression for the marginal cost, C prime. Well, that just means take the derivative of this using the power rule, which we can do that now. The derivative of the constant 900 is 0. The derivative of a linear term is 18. The derivative of this, the 2 comes down. That's where the 0.2 comes from. And then subtract 2 by 1. That gets us 1. And then the derivative of the final term, the 3 comes down. And then that 0.0002 times 3 is 0.000 times 6. And then the x cubed becomes x squared, because again, we subtract 1 from the exponent. So it kind of looks like a crazy word problem, but it's just saying take the derivative. And we're good to go. Okay, and then part C is just plugging in a few X values. The marginal cost for producing 50 lithium batteries. And we just found in part B that the marginal cost meant the derivative. So we're just going to plug 50 into the derivative, and we get $15.50. Plugging 100 into the derivative, that's the marginal cost. Plugging 100 into the derivative, we get $10. That kind of makes sense, because the more batteries we produce, the lower the cost is. That actually makes a lot of sense in the real world. As we increase our production, the marginal cost reduces. It's kind of like when you buy in bulk, your cost reduces. When you produce in bulk, your marginal cost reduces. That's the real world implication of marginal cost. Okay, so that is everything about the power rule, including some trickier applications, and you're going to do some practice between now and next class. Have fun. Let me know if you have any questions. See ya.